There's a lot to talk about, so I'm going to cover a range of topics because we spent some time talking about applications previously, but it is really important to understand that computational science has a range of different things that it does, right? That it helps with experimentation, it helps with reduction, it helps with an understanding, it helps with really supporting innovation as a broad concept and context, right? And because of the transferability and the ability to do what we call multi-scale models, it can really help both businesses and researchers understand science better. Now, Material Studio is an extremely comprehensive product. Accelerus has been around for a number of years. I've actually worked in this field for over 21 years now, right? And so the date actually that the presenter gave is actually the public foundation date of Accelerus as a corporation. We were around for a number of years before that, and I was actually part of that predecessor organization. And so we've been building modeling and simulation platforms and tools, and also developing our own codes and algorithms, but working with leading academics, such as the group on our pharmaceutical side, which is the Harvard group who produced CHARM, and in the Material Studio sense, with people like Bernardelli, the Paul Scherrer Institute, and the Cambridge and UK-based CASTEP development group, the Cambridge Analytical Serial Total Energy Package. So we've done a range of different developments. What we've built in Material Studio is a framework application that allows you to do both quantum and atomistic and mesoscale, and to then output results through statistics and scripts to give you pseudo bulk scale results. And it's quite important to realize that Material Studio covers a range of different tools, a range of different capabilities, and in fact, because it has this scripting and what we call platform support, you can actually interface it to nearly any code you want. And we gave a public webinar in the United States with CNE News earlier on this year that's on our website that goes through a lot of this extension and extensibility. It's a pretty complex architecture if you delve down into it, but we have this capability to connect. So we have users who run games, who run lamps, who run external data sources or literature or structure reference sources, and then bring those into Material Studio, and they can script that process. Less of that. Let's focus specifically on Material Studio right now. So Material Studio as a general interface. This is it. At the top, like anything, you have a series of usual drop-downs that we would expect with a series of tear-off tool strips, right? Down the left, you have what is a project. And a project allows you to have multiple folders and structures. So if I show you my copy of Material Studio, it looks very much like that slide, right? There's a series of functions where I can open, create new project, generate here under the file menu a new document, and I have a choice of documents that I might wish to create, which span all the way from simple three-dimensional atomistic structures through what we call mesoscale, where now I'm not dealing with atoms or electrons, but dealing with spherical entities that represent segments of, for example, a polymer, where they have a mean field type interaction. They might be textual, they might be HTML links and references, they may be grids, or which are more like Excel files, or chemically and structurally enabled variants of that called a study table, where I can have multiple structures within that environment. They might even be something like a force field document, where Material Studio has the ability, within certain limits, to import types of force field documents into a project, and on a project-to-project basis, customize those or edit parameters. And we'll get back to that a little bit later on. But again, just as I showed you on that slide, as I create documents, they appear within my window. When I go into that document, I can now do something as simple as apply, basic sketching. If I hold down the Alt key, as I just did, I get a unsaturated ring. If I don't, I get a saturated ring. I can obviously select different sizes of rings like this. I have a simple tool that allows me to continue to do that. If I make a mistake, I use my Control-Z undo, and obviously I can sketch linear atoms or more complex atoms, and I'll come back to all this in a second. Notice that I can now select bonds and select the whole of an entity, or I can just select an individual bond like that, and then I can start to change things like the bond order, the structure. And self-evidently, I can do things like cleaning and tidying and modifying. So I can select all of that and clean up the structure and then hydrogenate it and then clean it up. Cleaning is, as you see, a geometric, very simple representation. It's not a full energy force field. I would obviously go through to my force field technology here if I wish to do a minimization. But again, I can add new structures, so I can import a file from an example or a structures folder. So let's do something slightly more interesting, like a metal oxide structure, like a chromium oxide rhombohedral, and I can view that and see that within my system. And obviously, like any Windows application, I can tile these vertically side by side. This is the interface. I have tear-off modules, which can do different things, like my pointer, go to the home view of a structure, right? Scale the structure to fit it, or reset the view all the way back. I have my sketching, and these are all controlled under my toolbars options, you see. So I can have different toolbars on or off as I so choose, and I can save that as a preference. So far, I've shown you a little bit about Material Studio and just given you some, at least, orientation about how the interface works and what it does, right? So now what I'm going to do is I'm going to continue back with the slides, right? And we'll carry on. Right. Wrong slide, so it doesn't matter. Give me 1 second to find that appropriate slide. So, as you can see, there can be different types of documents. When Material Studio does a calculation, it takes a structure file, as I've shown you building, and it creates a subfolder. So if I do a semi-empirical using the vectorized Austin model potential set, Austin model wave function set, developed by Tim Clark and extended by many scientists within that group, vectorized AMPAC can be done, and it creates its folder as you see here. And if I did a separate calculation, it then creates another subfolder within the system. So, summary, there are tools, there are files, there are figures and tables, there are properties, as you saw in the bottom left of the screen when I was live and executing. And in the bottom center, there are jobs. Material Studio can be run as I do tonight on a laptop. It can also be run client-server to a parallel server farm or a cluster, or a range of different servers, in fact, as long as you have appropriate, licenses and modules and tokens. And you can then farm out jobs, and it has a little gateway mechanism for doing that communication over TCP/IP, over Internet protocols. And you can view where those jobs are running and what their status is in that window in the bottom of the screen. Drawing a molecule, as I just showed you, is as simple as creating a new structure, connecting or selecting the pencil drawing tool, as you see here. There are multiple ways of doing that, right? I can sketch a bond and sketch over it twice, or as I showed you, I can select the bond editing mode and change that to a double bond. I can draw my ring, as I showed you. With the Alt key, I can make it aromatic. Without the Alt key, it becomes simply a saturated ring. And I can then select different elements with my pointer key, and using my periodic table representation, I can change that. So within the application, right, right, this is done in the same way as I just showed you. I just go into my structure, as you see here. I might select one specific atom. I go to this periodic table to modify element. I have a drop down where I might make that an oxygen atom. I might also make that a chlorine atom as an alternative, right? If I make it an oxygen atom, I obviously now, as a chemist, have an unsatisfied valency that I find unsatisfactory. If I hit this, which is the adjust hydrogens, right, it then adds another hydrogen. And then if I use this, which is my simple bond length and topology cleaning mechanism, it changes that. Again, one can change bond orders as well in this. You can just delete that hydrogen. This is trivial stuff. I can select that bond and I can make it a double bond, right? And then say, now I can start to go in and delete and sort out my structure. The hydrogen fix sorts out my valency, and then I can do my cleaning, and you notice now that sp2, right, carbon becomes pseudoplanar, right? So now I'm starting to get a delocalized structure there, ketone, orthopolymerism, etc. Okay. This was the sketching we were just talking about. Where we go from sketching is the adjustment of hydrogens, reasonable geometries, and then we can start to save files. When we have files in Material Studio, we can output them in a variety of formats. Those formats include standard coordinate files, PDB files, a range of different formats. We can also, with material scripting, you can go into the underlying coordinate data model and extract them in any way you want. You just have to then define through Perl a simple Perl formatting. So Material Studio supports Perl programming, and there's a full API, which we'll come to later, where you can actually do those sorts of modifications and do it. That's why we have Perl script documents here within the types of files. Similarly, I can read in structures. I can read in a range of different file formats, or coordinates, and process those within the system. The file menu that I showed you very quickly live in the software has these elements, right? Really, there's importing and exporting, there's new structures, and then there's the other thing, which is where I can have multiple projects. So I can switch between one project where I'm working on a series of structures, save that as work in progress, and then move to another project when I'm working on it. For instance, if I move from heterogeneous systems to homogeneous systems, I might move from organometallic or organosiloxanes to organomagnesium systems, to organotin and lithium systems, and I might want to keep those for personal reasons or research reasons in separate folders, right? Display styles, well, I can change those. It's really very, very simple. You can just be within the application, you right-click, right? You can go to your display style. Within the display style menu, I can make things ball and stick like this. I can make them CPKs, right? I can make them polyhedral if I have an inorganic, and I'll show you that in a second. Or I can just make them pure sticks and cylinders or back to lines, right? Similarly, as you would expect, I can do that for bits of the structure. So this section, I can make ball and stick. This part over here, I can make CPK. And yet I could select everything else and do it another display. So this is one set. The other option is if I go into this inorganic system, the chromium oxide, right, where I can zoom out. This I can represent in a polyhedral mode. Let me just move that menu out of your way so you can see it. I'm at low resolution because for the webinar we're at 1024, so it's a little cramped on the screen real estate, by the way. Notice this also brings up another point that I made already in the slides, but I'd like you to understand that these explorers allow me to look at the properties of any atom. So here, I actually see that this atom that I've imported, this three-dimensional crystal structure, I can see that I have a fractional XYZ, I have a hybridization definition, For example, in the polymers, it actually tracks, is it a backbone structure? I can do partial occupancy. Material Studio has the ability to calculate things like X-ray spectra. That's done, and I'll come back to it, but it's done very simply through our reflex powder diffraction technology, right? That allows me to calculate the spectrum for any structure. And when I do that, and this is just, I just scrunched it up, but that structure now has given me a spectrum, and I can then sometimes, I'll just move that from the project, have cases where I have a partially disordered aluminium site, such as a T site in a zeolite framework, and this allows me to map atoms to have partially disordered and calculate them. Note, obviously, a force field, a molecular mechanics or a Newtonian mechanics representation of the system has to use a full spring constant, right? That's the way those are usually structured, but certain force fields can incorporate core shells, such as GULP does, the generalized lattice utility and programming system that we implement. But from a diffraction standpoint, you can have half an atom, and you can actually calculate the net scattering factors from that half atom within the system. Okay, back to the slides. Right. The first toolbar that is really important in Material Studio is the standard core toolbar that comes default when you open the product without any self-configuration. That just has the usual things you'd expect in any Windows app, right? New document, save document, import, undo, redo. Some Control-Z, Control-Y work on the keyboard. They also work within the interface, right? Very simple, very easy. The second one that is pretty common, and you've already seen me use it, is the sketching toolbar. This allows me to do sketching of rings, sketching of fragments. There's a fragment library built into Material Studio that includes some metal geometry templates, such as octahedral, tetrahedral, trigonal bipyramidal, square base pyramid, things you tend to come across when you're dealing with complex metal organometallic structures. And also supports things like cleaning, hydrogen bond building, modification of bonds, and some more esoteric things like centroids and templates. The third main core toolbar you have to look at is called the 3D viewer. That supports the selection, i.e. your cursor, translation, zooming, scaling, right? Main modules. This is a list of them. You can get to this two different ways, and it's sort of important to spend a second and pause on this. The first is that you can get to them from the modules pull down. For those of you who are a little old school, like I started, with Fortran 77, so that dates me, right? You can go to a Windows standard modules pull down, select the module you want, slide right onto it, select the function you want, whether it's the calculation or the analysis, whether it's the setup or the complex analytics on the back end, right? Each module has pretty much the same grouping, which is preparation, calculation, analysis, and reporting. Each module, and it's alphabetically listed, self-evidently, as you see on the left there, has an icon that represents what it does, basically, right? So just looking at this, if you follow my mouse, absorption sort of looks like an ethane docking to a surface. If you sort of think about this turn 90 degrees, right? A little bit of a challenge there for you. The amorphous cell is about packing polymer chains into an amorphous box, right? So that's meant to represent the box with the chain in it. Blends is supposed to be doing pairwise compatibility calculation between binary pairs using Monte Carlo theory. So blends looks like pairs. CASTEP, well, CASTEP is, as I talked about, one of the main plane wave DFT calculation engines or suite of engines behind the Material Studio interface. And at core, it's a plane wave DFT code, so these are waves. The Conquest interface is for those of you who are crystallographers or hardcore structural scientists. You become interested in things like doing work with structures extracted from CCDC, right? And this is the menu turned sideways. Here we have conformers, where it's meant to represent rotation around torsion. DMOL is a plane wave DFT, orbital type calculation, wave function calculation, suite of tools, so it's an orbital. And then we get over to things like particle dynamics. We get into things like foresight, where we have symmetry. We get into calculations of morphology and crystal habit. If you know that area, you know they tend to look prismatic like this. one step, which is an order n calculation, that's an n supposedly. The reflex diffraction down to things like absorption in zeolite pores, and the vectorized Austin model semi-empirical code called BAMP. So again, these icons also are the icons you will see in the folders for the inputs and the output files. Okay. Within the tools pulled down in Material Studio, there's a range of functions. Stuff for doing surfaces, stuff for doing reaction previews, which is very important if you have two structures and you want to estimate a trajectory file, just simple estimation that lies between them. You build one, you build the second, you tell it this is the first one, this is the second, this is the atom mapping from the starting to the final structure, and the system goes away and geometrically interpolates those and constructs a very simple series of structures that lie on that pathway. Now, what is interesting about that is that then you can take that into a transition state, nudged elastic band, linear synchronous transit, or quadratic synchronous transit mechanism, and start to do iterative calculations on each of those points and say, am I actually converged at a minimum, or am I a long way from that minimum, and how does that work? Okay. You can also customize the settings in Material Studio, so you can save your settings for each module if you have a set of preferred algorithms. Say, I'll show you in a second, I'm working within VAMP and I like a certain specific Hamiltonian and a set of convergence criteria, and I wish to use those and apply those systematically and consistently without having to remember all the nuances of my settings. I can save those, add to those, and I can manage my service as well. All right? And that's what happens within individual modules. The settings are done by a module basis for various functions, such as analog construction, mesoscale building, nanostructure building, polymer building, etc. Material Studio, and I'm going to keep moving because of the time constraints that we're working under here, has a series of builders. These range from basic polymer building, stitching polymers together, A, B, AA, B, etc., whatever A and B might be, and there's a range of those, I'll show you, through analog building, where I take a core and scaffold approach, and I take that core structure and I append to it a range of different pendant units. One, so I take my aromatic ring and I can put in the ortho, meta, and para different series of functional groups to generate a whole series of analogs. This can be very important where people wish to screen molecules, where they wish to test a hypothesis, where they want to run a calculation across a range of different substructures or structures within a standardized approach. There's also mesostructures, right? Obviously, we're starting to touch on the idea of multi-scale modeling in my introduction, mesoscales being the step up from atomistic, quantum atomistic meso. And there we may take beads and we may put the beads into something that's a football that may represent a micelle. We may actually have a core of that micelle that might be, for example, in the published work of fluoronic polymers, might happen to be an active drug substance like haloperidol. And around that, we might have to have a fluoronic polymer, which is an AB and ABC mixed polymer system. And so in that way, you can actually construct those and build your beads based on atomistic parameterization, and then feed those in. So that's all the area of mesostructure. Obviously, we can build crystals. From those crystals, we can cleave surfaces. We can build layered stack structures from those, and I'll try and show you that as well. But that's all the builder's side of it. So very quickly, I'm going to touch on 2 or 3 of those in a minute or so. Right, so first thing, let's just keep these structures. Every time I close it, because there's a star, it says, do I want it as part of my project? Yes, right? And so it saved it. This one, this atomistic thing that I've been sketching, you know what? I don't like that name. So I'm going to call it my mol, right? Now it's called mymol.xsd. And if I close it, it says, do you want to save it? And I say yes, and now it's saved. And that's part of my project, right? What I can do is I can build a polymer. I have the choice when I build my polymers, homo, block, random, dendrimeric structures. So for example, I can build a dendrimer, right? I can create a new dendrimer. I can just pick the seed as ammonia. I can set the repeat unit as 3,5 things, and I'm going to build 2 generations of that. And it goes out and it builds, there's my core, and it's built my multiple substructures. Just to show you that again in a different way, I'm going to build a more simple system. and I'm going to branch it out 3 layers this time, right, on top of that core. Yeah, don't like that, so select all of that, hit my delete key, I have a new one, I'm going to try again and create a new dendrimer, this time, right, I'm going to build it, and you see here it's built my acetylinic sort of propellerine, as you might want to call it, and it's just called it dendrimer 2. I could actually get it to name that if I want as well, right? But that's how you build dendrimers. Equally as much, you can go in and you can build polymers. So we could build a random code polymer, and the repeat units that I select, I can select from my base library of repeat units. So I'll select some isobutene, right? And then I will go in and I'll select some dimethylsiloxane, not necessarily fully chemically compatible, but now I can have it, and I can set the probability of having inversion if I have a chiral center, right, with an iso. I can build this by reactivity ratios versus probabilities if I want. I can enforce concentration. I obviously have my probabilities of what follows what, and I can weight that by just typing in here. I can look at my reactivity ratios, and you see here it is a 1-to-1 reactivity, but again, I can say that's a 0.5 relative reactivity, right? And so now I can build my polymer, and it constructs it, and notice, in this case, I told it to auto-name, so it's called it random isobutene dimethyloxane, right? And there's my polymer system, right? And there's my other chemical system, right? And these, the first thing you'd probably do with these is then you'd go in and you'd go to your foresight module and you'd go to your calculation engine, right? And you'd do an estimation of energy, or you'd probably do something more interesting like a geometry optimization. And just for the sake of time, I'll do it at course settings, right? I'll hit that, and if you notice, it'll set up a few files. It'll generate, right, my foresight calculation down here. It'll say it's running. It'll run for a second. These graphs are horribly squashed, and I apologize for that. That's just purely because of the screen resolution, right? So it's now completing and downloading the results. It did it so quick I couldn't even get to show the chart, right? Just again, what did it do? Well, it took that, it minimized it, right? It did some energy minimization. It did it by reducing forces within the system and resolving them from very high at the beginning to far, far lower as it moved down the curve. And that's not a great graph, so we'll just sort of close that one. We'll look at the convergence system, right? And so now you see that it actually converged rapidly and then tailed off as it did what is called a smart optimization, right? The resultant structure that came back is this one, right? With my potential termination atoms there and looking at possible connections. Notice that this folder is the calculation that came from the dendrimer. So what it did is to take that original starting structure, copy it over, run the minimization, apply whatever trigonals, and it might have looked at delocalization, right, onto that system and plot it. And what's important is you see here, this is the structure file. This second one is the setup file. So I might actually do any of these types of calculation, whether they be dynamic, whether they be annealing, shearing, confined shear, etc. Right? The other side of this is it's just the same if I take my mole here, if you remember, and I go out and I run a quantum calculation on it, such as a semi-empirical, very quick calculation just for the sake of demonstration. Here, I can set up a VAMP run, right? And notice it starts executing. It'll run that. Let's just close out the little bit. So we've got some more screen real estate here, right? Save that into the project. I'm just closing a few of these. You can stack them, right? It's completed the calculation, right? And it's done, a simple one here. With the VAMP module, I have the ability to do analysis, right? And I can bring back molecular orbitals onto that system. So obviously I can look at things like my basic set of those, minimal spin up, spin down set, bring back the highest occupied or the lowest occupied molecular orbital, just run the import there, and there's my LUMO, right? And There's my HOMO as well. And this brings me to another toolbar, which is the volumetric selection. That allows me to turn off and on ISO surfaces like this, right? I didn't actually develop it for you. Let me do that. Where's my HOMO gone? So let's just look at the orbitals, isochrome molecular orbitals, right? Hit import from the file. There it is. So now under my volumetric surfaces, I have HOMO, or I have LUMO, and I can change those. I can change the surface colors on those if I want. I can do all sorts of things with those and manipulate them at my leisure. Right? Oh, and obviously I can insert planes on this system across one of these materials and surfaces, right? And so those planes are volume elements, as it were. I can select them. Right? I can manipulate or drag or change their position if I so wish, or the view on them. Right, so that allows me to do things like that. And those can actually be stepped as well. So I have the ability to do step translations or modifications or changes, or I can twist those slices and fit it parallel to the second axis and look at fields mapped onto those. That's showing you the extent of the HOMO field that I had and the value index. And you can see here that I have a color range. And I can control my color ranges even within that surface. So actually, I can take out all of those and all of those. And now I can actually switch out specific colors and generate sort of punch-through holes, as it were, in my surface. This can be used on orbitals. It can be used on surfaces. It can be used on maps. It's a general purpose function through the ISO surfacing and rendering fields and capabilities that Material Studio provides. All right, different builders. Building tool environments are sort of context sensitive. I've shown you dendrimers, I've shown you polymers, I can touch on crystals and surfaces. Obviously, we have nanotubes, nanoropes, nanoclusters. You can build multi-core nanoropes very easy. These are the polymers. We've touched it. These are some more examples where I'm now dealing with block copolymers, homopolymers, right? Random copolymers between materials. As I've shown you, dendrimeric structures. You can define repeat units for that construction, dead easy. You can define branch points. So here you see I have a head and tail branch point. If I so wish to build a repeat unit, force field minimize it, quantum minimize it, and then define a polymer from that, I can then choose exactly where that extends within my polymer frame. Right? Crystals is really easy. You build a box, you tell the system what symmetry from standard international tables, space group symmetry. You define various, if there are origin choices for central symmetric space groups, etc. You define those. You define options such as unique axes, right? P21 upon C, P21 upon N, etc. And you build those. Here's the lattice parameters. Here's the options. C is unique, right? The AB plane is projected on the basal axis. You can also, when you're building, check for atoms on special positions so you don't get the case you have an atom at 0.499999 and suddenly you have 12 copies of it clustered on top of each other. And that tolerance is a user adjustable parameter. Nanostructures, well, we have a nanostructure series of builders, so this is appropriate to the Institute and I think a number of people in the audience. This nanostructure builder is really easy. It's sort of simple. You can build nanotubes and nanoropes, just boron nitride or carbon-based systems by defining the translational vectors as you map out of the graphene layer. Things like nanoclusters, you have to have an input crystal structure, and then that becomes defined by the nano builder. You can build frustrums, you can build polyhedrons, you can build dumbbells, cylinders, squares, cubes, spheres, etc. So here I'm defining again by n vectors, whether I have a chiral system or an achiral system, right? You can hydrogen terminate your chain. If you wish to build caps, we actually, on the accelerist.org community website, there have been a number of people posted mechanisms or methods or approaches, both script-based, force field-based, geometric-based, for capping these with rounded caps and systems. The other point is that's quite useful is if you go to high N over M, where you have very, very corkscrewed nanostructures, it becomes quite critical to be able to know that you're building something that's 1,000 angstroms long. That's going to be a bit tricky to do calculations on or minimize or fit in a cell box. Multi-walled nanoropes, just done the same, nanotubes. And we can do nanoclusters. This was actually developed by the Nanotech Consortium that Accelerator ran successfully a number of years ago, and is thanks to many of the academics and industrialists that supported and worked with us on that. And it was their suggestion that we have this nanorope building and nanocluster building. The nanoclusters, it's important you can have truncation, you can have elemental substitution. So I can bring in a homogeneous material, and I can do element substitution along different vectors, different directions, and I can do capping of bonds. So you notice here, this picture, although looking homogeneous, or sorry, looking uniform from a crystal structure, actually there are various inclusions here, right? And you can have vacancy functions. There's the nano builders, dead easy. Those are the types of things, as I said, the types of structures that you can build out of it. There is one other where I can do coarse graining. This basically allows us to take repeat units defined within a polymer-monomer structure and to map those into beads and then keep track of where the mapping is. It basically allows you to build bead structures and to know that C2H4 happens to be one bead and C7H11 happens to be another bead. Okay? Right. That's the first part of the presentation done. Just not say that. The second thing I wanted to start going into for you was a little bit more into this building stuff, right? I think we'll actually go over that. One of the core parts of Material Studio is its ability to handle force fields and force field systems, right? These, in essence, you can do conformation analysis, molecular dynamics, minimization, Monte Carlo simulation, step analysis. You require a force field parameter set, you require a structure, you require parameters, right? Molecular mechanics, everyone knows, there's a set of springs. There's a whole complex series of parameters that go into a force field, whether they be just linear extensions, angular extensions, torsional extensions, outer plane bending extensions, what we call improper things that keep, ammonia, pyramidal, etc. And they have different functional forms, right? The choice of force fields can be quite extensive. There are many different ones that are defined within the literature. Sometimes it depends on whether you're dealing with Morse-like potentials or harmonic potentials are good enough, because harmonic potentials are derivative and easy to analyze. Morse potentials are a little bit more complex, take longer to invert, and therefore calculate. Basically, there are parameterized first and second generation rule-based force fields, and within Material Studio, we actually support a whole range of different force fields. So we support CVFF, AMBER, we support legacy briding, PCFF, Compass, first, second, and third versions of that, the CFF, and those last three are what we call second generation. We also support rule-based force fields, the original Tony Rappé work on universal, and the ESFF force field, where there's been a number of different publications recently. What is important is that some of these have similar functional forms, and we actually support the editing of those, and obviously there's improved accuracy. So if I were to take one of our molecules that we constructed, or in fact, if I were just to import a new molecule, right? So let's just import a basic structure. Let's just go here. Let's take a simple example, such as a. Let's just do it the other way. Right. So as a organic, a 1,3 benzene, right? And then we're just going to run a simple, let's add some little chain to that, so it's a bit more of a challenge for it, right? So again, sketch, 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 connect, right? Add hydrogens, sort it out, clean it out a bit, right? Go to my modules, go to my foresight tool, go to my foresight calculation, geometry optimization, let's just do it medium, right? Notice that I can set up with different, so let's just try and run compass, right? Let's just check that runs. See, I've got parameters for all those systems, right? Sets it up, runs the energy minimization, it completes very quickly, right? Because the energy server is very fast, right? And what it's done is to generate me my file and output my structure, right? There is my resultant structure. Easy, simple, done. Now, one might wish to edit a force field. So, for example, if I was using writing for my minimization or CDFS, right, I might want to bring that into my project like this. When I do so, it shows me the reference to it. It shows me the types of atoms that are defined within the force field context. It shows me a number of those interactions for, say, angle bend terms, X being an NNIN atom, or torsion terms, right, dihedrals. It shows me that I can sort of look at different functional forms. I can set parameters. I can apply modifications. So there's a polynomial order, sixth order. I can change that. And I save that as a local copy. You see here, now there is a force field file copied from the reference set that's always locked and protected in Material Studio, and it's written into my project. Now, similarly, for those who are interested, I can import, right? And I can import different structures and files, and I can do different modifications, or I might bring in a force field. Okay? So that's one of the ways that you can extend, modify, customize, and change your force field parameters from that, right? Again, sometimes force fields comes with charges. You can override the charges. That's an advanced feature in Material Studio. So coming back into this calculation, if you remember, I showed you that when it creates the folder here with the name of the file and geometry optimization, it copies in the input, and then that becomes modified by, say, minimization, by deformation, by the quantum engine. It also brings in here, right? So first of all, I'm just bringing up the structure, and then on top of that, I will bring up the input deck, right? So this is the input deck, and it makes a copy of it, and when you click on that icon, it just opens the panel, right? And that's very important because I can look at all the settings I have. I can look at my engine, right? I can look at my charges, whether they are the current ones. Say I've used a quantum calculation, and I have done something like a Mulliken population analysis and put those charges onto the atoms. Whether I, in fact, want to just manually go in and select that atom, right, and go here to my property window, double click and say, you know, I don't like that charge for some personal reason, some research. I want to see what happens if I make the charge to that 0.2345, right? And I apply that. And you can see that because I can label everything with the charge, right? So apply that. Then I can see that I've got that atom labeled, just deselect and apply it to, select charges, apply to all atoms. Now you see I have everything labeled, and I can remove all of those, right? And I can then run my calculation and use the current charges if I so choose, or run something like a charge equilibration gas diagram method, which is relevant to the universal, or I can use the force field assigned charges. What's also important is, within the force field, I can actually look at the atom types. So we all know in the molecular mechanics sense, if you are an electromechanics person, that there are different force field types, and sometimes you want to investigate or look at or reassign what an atom typing engine, which is what Material Studio has, and it visualizes, it sees a set of atoms and you call a force field. It says what atom types are available. These are what I know about the connectivity, topology, and hybridization of those. Therefore, I assign these atom types and formats to them. All right. So you can go in and you can see all those atom types, and you can show only the ones that are relevant to that structure, or you can list every single one in the force field, right? There's different options there. You can change those, right? And there's job control. So when I run a calculation, you probably saw that it just had a funny 6-letter number mnemonic associated with it. You can, if you're running multiple queues, say, no, this is calc 1, this is, calc n, right, etc., whatever I want it to be, and then it will appear in the queue, and everyone would see that it's Michael's calculation, MJD underscore calc 1, calc 2. I might define my jobs as, etc. Right? Remember, the same structure, you can run multiple iterations and calculations. This little project that we have here, I first took this structure, right, and I ran a BAMP calculation on it. And that gave me a geometry. Then I ran a force field calculation on it. And I might actually go the other way. I might take a raw structure, run a force field calculation, then run a semi-empirical calculation, then run a DFT calculation on it. Of course, if you note that the big key point about Material Studio is I can do all this for solids as well as molecules. So I can import into this, instead of an organic, I might import a semiconductor. So I might import something as simple as a silicon carbide lattice. Right, there it is. There's silicon carbide. Right, click on the silicons. Yep, there's an RGB silicon. Click on the carbons. There it is. If I press the Alt key and click on one, I get all of the should get all the atoms that are similar. Right? And so you see now I've selected all of the carbon. That is a tool, right, where I can go in here and I can do my selection, modification, right, under my edit menu. Atom selection, I can do things as simple as showing me select all the carbon. See the yellow things are selected. Or I can select all the silicons, and I can select those. So you'll see now, just zooming in a bit with my middle mouse, right? See this silicon here? I can do a selection on it, right? That's pretty trivial. What is interesting within a system is I can say, select me everything that is a radial distance from a specific location, which might be the origin, right? It might be a specific point. It might be, I want to know everything that's within 1 angstrom of that atom that I've selected, right? And that says, nope, nothing. So I go out to, say, 4 or 5 angstroms, and now I'm starting to get a spherical. That's important where you want to start defining regions or subsets. And when you've defined that, you can define it as a set. So now when I have a set of atoms selected, I can create a new set from those atoms. It happens to be called Michael set, MJD set, right? And now I have an MJD set of atoms, which is the ones that are highlighted and selected. All right, I can just obviously delete that set as well. So this is all the molecular mechanics. It's very easy. This is what I told you about charging. This is what I told you about force field assignment. I'm not going to waste your time going through all of the basics of molecular mechanics, but it can be done. Equally as much, I can do this within periodic boundary conditions. So I can do minimization on a periodic structure or an amorphous cell structure of a polymer. It's considered the center of a 3x3x3, i.e. a 27-box grid, where polymer chains that extend through the boundary face become re-entered through the other face, where van der Waals interactions can be considered across the boundaries, where obviously you have to take care of charge representations within the system, so that allows me to do that, right? I'm just going to stop talking about all of that molecular mechanics for a second, and I'm going to go on to talking about another area, which is the idea of building amorphous polymers, and then I'm going to talk a little bit about the semi-empirical and the quantum field quite quickly. Amorphous polymers are a very big area for people. It's a set of comprehensive tools for building these, right? I've just explained periodic boundaries. Single chain representation is in fact a 3 by 3 by 327 cell. How do you build it? How do you make that happen, right? Well, what you do is you basically just grow a chain. When it hits the boundaries, it re-enters, it keeps growing, it re-enters from the other facet, and it does it. Amorphous cell allows us to do it. It's actually a very intelligent set of algorithms and builders. It does multiple configurations. It does those energies. It does those builds. It starts with multiple chains in multiple places. It deals with things like ring catenation, which is always a problem when you're doing Monte Carlo builds of organic systems, right? It removes those and checks for it. That's an option. It allows us to do low density construction and then compress it with NPT, microdynamics, constant number of atoms and uniaxial pressure, right? Note we can also do shear molecular dynamics inside the force field engine in the Behrouz Studio, right? And we have a series of protocols that allow us to do it. This is the confined shear, where I apply a force or a velocity or a vector or an energy content to what are called boundary and wall atoms, and that allows me to look at slides, etc. Basically, the workflow is this. You sketch your components to make your polymer, you build your 3D geometries, you define your charges, you say how many of those I want to grow in my amorphous polymer. That tells you what's the density, you define the number of initial configurations, and you basically set up a bunch of little preferences, which you can use the defaults out of the box, or you can customize them. That allows you to do look-ahead catenation, refinement, and then you can go through your own minimization and calculation. The sorts of calculations are dynamics, where you can look at vibrations, compression, shears, and tension. So that's what you can do with this. The sorts of analyses that people sometimes do are things like pair correlation functions. These are built into the analysis inside the Foresight system of Material Studio, where you define a spherical shell thickness, you look at the radius, you look at that, and you calculate the pair correlation function between them. The scattering curves, where you're looking at isotropic ordering and disordering. The mean square displacement, where you're looking at the diffusibility or diffusion of small atoms through those. Again, all of those, just to be clear, are accessed from the modules, right? Foresight, which supports symmetry, right? Analysis, and the Foresight analysis allows us to look at, if I have those dipole autocorrelation, functional length, mean square displacement, pressures, radius of gyration, as we're talking about, the scattering functions, the space-time correlation functions that I've done a dynamics analysis. These are structural, by the way. Notice the ones that are applicable to a given structure without a dynamics trajectory of being calculated are black. The ones that would then come into focus if I had run a dynamics would be then gone transition from gray to black, right, etc., etc., etc. Right? And again, notice that the Foresight engine, as I keep saying, but I think it's very important to emphasize, works if I select a force field such as something like a universal setup. Just do an quick energy calculation on this. Do I leave my settings? Yeah. Right, hit run, and it will go away. It will set it up, right? It's done a calculation, and it's done a simple setup of an energy evaluation. I can look at that decomposition, right? So that's the first part of all this. You can build structures, you can then go in, and now I want to talk a little bit about semi-empirical and quantum theory for a minute, right? Force fields, I think everyone gets. It's pretty obvious. Everyone understands Newtonian mechanics. Semi-empirical theory is basically simplifying all of the diagonalization, or a whole bunch of diagonalization terms, and to reduce the computational problem that you have in quantum mechanics, where there's a lot of overlap and a lot of difficulty assigning those overlaps in a self-consistent field approach, right? There are parameters in semi-empirical theory. There are different sets of parameters. Some are called modified neglected differential or diagonal overlap. and this allows us to do certain systems, but doesn't really take into account hydrogen bonds, ionization is a little bit off, etc. Then there's a correlation effect change on those, right, where we can actually start to look at transition states. We can start to look at things like this, but I built a Diels-Alder system, right? This has been around for a while, right? This is not new technology. Then we start to go into things like the Austin model, so we correct some of the problems in MINDO-C. We had Gaussian functions, you notice our parameterization is extended, right? These are the improvements, which are energetic, numeric, right? There are limits to the Austin model, right? It doesn't do very well with things that go boom, that people sometimes interested in, called nitro-type compounds. It doesn't do very well with some of the peroxide bond systems, the oxygen bond systems, and some of the carbon-nitrogen bond rotation barriers. So what was then done was extensions of it, where they added some additional parameterization for some of these elements you see starred in here, right? And copper and zinc were actually added way back in the Material Studio 4.1 version. So this then gives us, you know, a series of molecules or base systems, chemical systems, well parameterized over those, right? It does well, but not quite on the hydrogen bonds. And that brings us to the PM3 model of Jim Stewart. And here you see the corrections of that. And the child of PM3, which is now called PM6, where it covers most of the main group, and it has significant improvement for hydrogen bonds. And PM6 does pretty well if you see the modifications and accuracy, the error rate over a range of different chemical species, the 6, 5, 3, and the original Austin model, right? If you're interested in metals and things that have beyond S and P-like functions, where you think about d orbitals, where you're doing the second row, then you use MINDO-D, right? Heats and formation are better, doesn't do a great job on ionization potentials because of that electron modification. There are a couple of other semi-empirical parameter sets implemented within Material Studio within the VAMP engine, which are Zerner's intermediate effect or differential overlap, which is ZINDO, CNDO, INDO, right? And these allow us to do spectral predictions. There's obviously CNDO, which is complete neglect of differential overlap. It's the crudest, it's the least accurate, let us say, from a chemical standpoint, but it does pretty well, right? So VAMP is the engine. It does pure energetics, which I've shown you. It does geometry optimization, which I've shown you, and it does transition state search, right, which is a saddle point, a McIver harmonic transition state optimization from geometries each side of the barrier. The setup, just the same. You select an energy. You can set different transition state following tools. Note that it does restricted Hartree-Fock, unrestricted Hartree-Fock, right? And you can set spins and spin constraints on the system, right? There are different convergers that can be used within this framework and system as well. And then there are things like different shift control systems and different smearing schemes that can do it. For users who wish a quick capability, what I mean by that is you just want to go in, do a calculation at a good, easy, a basic, reasonable, or high precision level, good, easy, or simple, right? They can just select it. And that is set from the setup, right? That then drives a whole series of configuration down in the convergers and the other parameters, and that allows us to do those interactions, okay? Also, we support Cosmo for self-consistent field and self-consistent reaction field calculations. And you can set that, Cosmo being a dielectric continuum that represents the extended bulk solvent. Similarly, with amorphous cell, you can build an explicit solvent, and in fact, you can do an overlap between the two, because amorphous cell allows you to build within an envelope. So I can take my molecule, I can build a van der Waals envelope at 6 times van der Waals radius around it, and then say, drop me a few waters within that, and then outside that, put a dielectric continuum. So I don't have to fill a huge box with waters, but I have both explicit hydrogen bonding solvation systems and implicit hydrogen bonded solvation systems as well. The workflow is this, pretty simple. sketch the molecules, select the task, select the Hamiltonian, select spin, charge, set up, select your convergence scheme, your configuration interactions, your solvent scheme if so needed, and then what properties you want, frequencies, localized orbital, UV vis, spectral calculations, etc. You press the button, the system runs, and it feeds them back, and then you can map properties. You can map orbitals, you can map electrostatic potentials, you can map isosurfaces, and then you can use that spectral punch-out tool to remove certain ranges and regions from that. Here, the orbitals, by the way, we can do localized or canonical, as I've said before. All right. Next sort of thing that you might wish to do is you might wish to do a more advanced calculation. That might be a DMOL type calculation. So let me just bring up those slides, right? DMOL is a density functional tool, right? So very, very quickly follows the same basis, but it uses the Kohn-Sham theoretical implementation of this, right? Where you're basically saying density is more of a transferable parameter than just the wave function. The setup is sort of simple, but there's this little part in the center where you can select the functional and the type of function. So you can do a localized functional, or you can do a generalized function. The local density approximation allows us to do things within things like metals quite quickly, but it also allows us to do calculations rapidly. There are a couple of different functions in that approaches. There's the Perdue-Wang and the Voskov-Filke-Musser, right? Approximation. We can also do generalized gradient approximations. These allow us a whole range of different extended systems. There's Becky, the Perdue classic one. We get from there all the way down to the McCandy, Bose calculations, and we're extending these. And we've added things like van der Waals corrections for the colligative effects and close order effects on high density systems and organic systems in lattice. This calculation DMOL is DMOL free because it's three-dimensional. It allows us to do periodic lattices or molecules with the same sets of Hamiltonians. So you can start to ask the questions of, does a molecule sit on a surface? What's the individual molecular entity? What is the bound molecular entity? Spin, no spin, multiplicity. The tasks are obvious: energy, single point calculation, geometry optimization, reduce the forces, do a self-consistency, calculate the charges, and then move it out. The geometry optimization, you can set convergence criterion by quality as a simple preset, or you can go in and set any of the individuals and you can drill down to that. When you're doing a unit cell, you notice here I have the option to optimize the cell or not, so I can do the molecules in a fixed box, or let the whole box start to collapse if the molecules start to fold in on themselves, and I create vacancies, vesicles, gaps, and densities in the system. Obviously, it does a geometry optimization step by force, then it does a self-consistent step, calculate electronics, then it does the forces again, and then iterate through that. Within the self-consistent step, it basically generates potentials from the atom distributions, it solves the Kohn-Sham equation, it calculates out the new wave functions, it updates those, it then says, have I converged? If not, it self-iterates. Once it's converged, it then goes back to the force calculation, resolves those forces, steps the atoms, and then goes to the whole thing again. And it does that until your net total convergence criterion is satisfied, right, or not. Note that it works within internal coordinates so that you don't get horrible ring flips occurring or torsion flips occurring. That means that the internal fields are r theta phi, and sometimes users, when they look at files, take a second to orient themselves around what those mean, right? Those are the plain choices where you have the potential, the kinetic contribution to the gradient function, and the value. Notice that you can do the potential with pseudo potentials or electron full potentials. These can be non-periodic, periodic, or symmetry driven, right? You can apply plane waves, LCAO, linear combination of orbitals, Slater type or Gaussian, or fully numeric, right? There's an all electron treatment within DMOL, right? And that's how the system functions. The other big energy engine in the last few minutes that I have left that I talked about was CASTEP. Okay, CASTEP was developed, and I've just really only touched on the engine. I haven't touched about on all of the range of applications, other applications that Material Studio support. CASTEP was built specifically for semiconductors, metals, minerals, solid states. It employs DFT, employs the pseudo-wave potential method of DFT, right? So in this, it allows us to look at periodic slabs and band structures and properties of that, right? Remember, when we talked about amorphous polymers, we talked about this. Well, we can also talk about a periodic cell where I have slabs and vacuum gaps and band structures within that, right? All of these presentations we can make available to you. If we put those together, we can start to get orbital splitting. So we need to take care in a metal system of conduction bands, valence bands, and the gap between those. And we start to ask the question, if we're building a semiconductor where we're starting to dope specific atoms in there, I'm actually changing that band gap to allow some population from the valence band to conduction band. That is a common question. What happens to this? What is the thermal consequence on my system? What is the electronic consequence on my system? How does that work, right? This is Material Studio. I can take a lattice within Material Studio, right, such as my silicon carbide system, right? And I can do something as simple as I can go into this, right? And I can look at the Brillouin zone path on that system. So I can just very quickly create that, and it's pretty boring because it's a cubic lattice, but now I can see the G vectors on that system. I can see the Brillouin path here in red. I can take that lattice and I can do a very simple calculation with CASTEP on that, right? So go into my plane wave. Remember, it's waves, right? And what we'll see is, instead of this having a symmetry, we'll then create a folder within that will have a set of waves. I'll do a very, very simple express calculation on that. I can run that doing my different corrections, different functionals, right? Just hit run. Okay, I wish to convert that to a primitive cell. It sets up my calculation. It's built my folder here, right? So inside that, it's done actually and generated my niggly primitive representation of that, because that speeds up the calculation. It then goes away and sets it up. It completes, right? It's done the calculation. There's the reference. This is just looking at the output deck of that file. Here's all the settings. What is important to realize is that I can save the input deck for this from Material Studio as well, and I can then apply hand edit in DMOL or other functions. Notice it just said those are my two elements, my atoms in my system. Here you see my fractional coordinates. It's now done my symmetrized force calculation. It's done my atomic population Moloch analysis, my Hirschfeld analysis, right? And then it's written out my results. Now, if you notice, that was a very, very basic calculation with CASTEP on a lattice, but I can select more properties. So I can calculate densities of state. I can calculate, the electronic localization function, or let's just do the band structure instead of that as well, right? And I might choose to then rerun it. This is important about Material Studio, that sometimes first-time users get confused. You see, I can't run anything. That's grayed out. That is because I'm not looking at a structure. If I look at a structure, now it's black, and I can run that calculation, and I can run it, and it creates another folder, a subfolder, you see, right? And that subfolder contains my starting structure, my parameters, my band set parameters. It's running the calculation now on my machine. I could have chosen, by the way, to run that in parallel. I'm only running on one core right now. I could have run it on 2, 3, 4, 5, 6 cores if I wished, right? And that would have run a little quicker. But it will converge in a minute. It finishes, right? It's done. And within that, now I can see my output structure, right? Notice it's representing my Brillouin zone and my path on that. I can go to my module. I've been going here for modules, old school. I could just say, no, I know what I'm doing. I'm just going to go here straight by wave function analysis. And on that, I just want to see what the band structure that it produces is. And I can view it. And there's my band structure. And this is a graph that I can zoom in on if I so wish, right? I can truncate, I can magnify or reduce, right? Or I might look at the density of states. And again, I could do the total density of states, or if I wish to, I could do partial density of states if I didn't do a full DOS. I just did a full DOS calculation. But there's my densities of states, right? There's my valence band. So again, this is how you do calculations inside Material Studio. It's very, very simple. It's very easy to use, and it's quite good. All right. I just wanted to do a quick time check where we're at right now with the situation. If the moderator could just tell me how.
Yeah, Michael, we're almost out of time.
Okay.
We just have enough time for Q&A.
Okay, let's do some Q&As and talk a little bit about calculations, please, if people would like to pose some questions.
Audience, you could post your questions now.
Right, that's right. That's awesome.
We have a question that reads, can you build crystals by incorporating additives using Material Studio?
Yes, absolutely you can. Material Studio allows me to just build crystals in two different ways, all right? So I'm just going to, inside this new folder that I made, right, showing you that, build a new structure. The first one is very simple, right? I can build a crystal, yeah? Sorry, missed that. Build a crystal. Okay, the crystal is this simple, right? It's a box. I can make the box as big or as small as I want, right? I can apply some space group symmetry to that. So let's just do one of the very simple, trivial, basic space groups like 2, 2, 1, right? And I can just say build. And all I have is a box, yeah? No one would argue with me. Now, if I now created a new structure in my, this is my additive. Okay, hang on. F2, additive, right? Everyone happy with what I'm doing so far, I hope. Inside this trivial molecule time, let's just do let's do a 600 from a demo standpoint, right? There you go. There's our molecule. We'll just hydrogenate it. We'll grab my pointer here. I will select the hydrogen terminus atom. I will then say, you know, I really want that to be an oxygen because I'm dealing with phenol. I'm now going to add that. I'm now going to apply a bit of cleaning, right? There's a method to my madness. I'm going to select that whole thing, Control A. You can't see it, but it's very easy, right? And by the way, just what I told you before, Control Z, say I decide I don't want that, and I get really sort of silly about it. I go, no, oh dear, how do I go back? Control Z, undo. See, Control Z, Control Y, goes forward, Control Z goes backwards. Control A, select all, Control X, cut, Control V, paste, basics. Everything should do this. If I go back to my box, I can go Control V here. And notice now I have two copies of my molecule, right? And I can select my molecule and do things with it. If I so wish, I can move it up. And you notice the symmetry is applied. I can move it left. I can move it right. Okay? So now I can start to put that molecule in there. Of course, I might say, you know what, inside this system, this crystal structure, I have an additive, and that additive happened to be, pardon me, a cyclohexane derivative. So now I have my cyclohexane, right, twist boat, version of cyclohexane, Control A, Control C, go back to my this, which I'm being very poor, I'll say is lattice, right? Experiment, right? Left side, that's obviously the French spelling, L-A-T-T-I-C-E, right? And go here, go back to my, oh, sorry, that's the additive. I'm renaming things. So this is the C hex, right? This one is the aromatic, and this one is the one. So this is called lattice. Okay. Now, I finally got it right. There. Now, right. Let me just. I got these all around. Doesn't matter. So now I have a crystal structure where I can select this, and I can move it around. I can manually move it, or I can translate it, right, and put those in the center of my lattice. Then I can select my basic molecule or additive or function and build that, and I can translate that around as well. And I can now minimize this and start to look at the ratio of incorporation, or I can build a bigger host lattice of this if I so wish, right? So obviously I could go in to my display style, into my lattice, and build out a 3 by 3 by 3 by 4 by 3, right? Okay, let me just, so this we'll call LAT, and this we'll call ADD. There you go. So you know, so now I can build this, and even once I've constructed this, and assuming you'll give me the caveat for the sake of time that I've minimized it, now what I can do is I can turn this into a large superstructure. So I can go in and say, you know what? I just want to take away all that symmetry and make it a P1 cell, right, in there. Or I want to take away the repeat and make that a supercell. So now it's just one big box, right? So this is how you start to build representative crystals. And when you've got a crystal material like this, you can then take advantage of the other part of your question, which might be, would something bind to a surface of this? So I can go in and I can do surface cleaving. So I can go into this and go 1, 1, 1, right, which is the body diagonal on this system. And I can cleave a 22 thick surface from that. Now I'm cleaved out a surface, and I can take that surface and then start looking at docking new tailor-made additives onto it. And that's actually a very important calculation, because it's quite easy now, once I've built a surface like this, to then take a new species, and my new species is the one you can see it's very small there, bouncing up and down, right? Moving it up and down here, can move up and down. I can calculate the energy on the surface. I can calculate the energy off the surface. I can look at the differential energy between the two systems. That gives me favorable error compensation, whether it's an approximation of my force field, approximation of my geometry, etc. And then I can actually say, this ranking series will actually interact with this surface. This ranking series would interact in this preferential way. So I can start to look at tailor-made additives onto that. The other aspect of that, again, that I can do is, if I have a lattice and I have minimized it in some way, I might apply a morphology calculation to it. So I might do something like a very simple Bravais-Freenol-Donny-Harker morphology calculation on that, which will take the geometry of the system. It may not converge. Oh, it did converge. That's great. And onto that, it will calculate an estimated morphology by actually doing a force field calculation and looking at the attachments, and it will bring back, you know, faces, DHKL indices, and look at the face area of that. Because it was a cubic and I hadn't done anything to actually skew it off cubic as a monoclinic file, we wouldn't have done it. Anyway, long answer to a short question. More questions, or follow up from that?
We have another question, and it reads, using only Material Studio, is it possible to create a sinusoidal surface roughness over a silicon cantilever beam, apply a harmonic load on the free end of the beam, and then perform a molecular dynamics simulation?
Yes, it's a little complex, right? But yes, it can be done. For example, just to show you that, if I built or part of that, right, because that's quite a big thing. If I save all the stuff I have in my project, shove it all onto my disk, right, which is what it's doing right now, and create a new project. And I'll just call this box, right? Box deflection. Right. Okay. So in this, the first thing I might do is I might import into the system a structure such as a silicon system, right? So let's just find SI. Right, within that, there should be an SI file. There we go. Right, import the SI structure. There's our silicon system. Now, two ways of building what you talked about, which is the big cantilever. One obvious way is I go to my display style, right, where I have lattice, and I make this 10 long. Okay, hit tab, and what I now have is something that's a cantilever system, right? Now that's an arbitrary ABC repeat. I could have done it the other way by cleave a surface and then extend the surface in a uniaxial manner as well. But self-evidently, I can take this and I can make a non-periodic superstructure out of it, right? So there you go. So now, apart from a couple of atoms dangling at the end there, which I can tidy up pretty quickly, right? That one, hit my delete key, you know, zoom in a little bit further, take out that one, right, do the same at the other end, those two are that two. Now, what I now need to do is to do a calculation where I would invoke materials script, right? What I mean by that is the following. I'm going to actually show you it, how I would start that, right? But it is actually very, very, very interesting. Okay, so let me just find that. Okay, so Material Studio supports Perl-based scripting, right? And right, so the first, just very quickly, basically the whole of Material Studio scripting. Let me just find the API definition, right? Right, this is the Material Script API. Every single entity inside here I can address with a Perl script, all right? So I can take the atom positions, right, and I can manipulate them, apply a sinusoidal displacement or a function to them using script. Using script, I can also run a systematic displacement to apply the cantilever force to one part of my simulation, and the other part of my simulation, let us say the anchor point here, I might go in and I might apply constraints and fix those relative to Cartesian space. So hence, I would apply my force to these atoms and I would have fixed these. Just so you see that the display style that I'm showing here is colored by elements, but I might actually colored by constraint, right? Did I apply those constraints correctly? So now you're seeing the constraint functions as gray and the unconstrained functions as yellow, right? That's the first part. Second part of this is that you can then force Material Studio to do repeat calculations iteratively. I just want to show you one simple example of that, if you permit me, right? In my examples file, you go into scripting. One of the ones that I like to show people because it's so simple, you'll all get it. Please bear in mind my computer's on California time, right? This is a Material Studio Perl script, right? Dead simple. What this does is it sets up a clock, and it builds that clock, and it iterates that clock, and it constructs it purely geometrically, which is exactly the way you would build your sinusoidal displacement on your silicon atoms. That's a series of silicon atoms that I've placed around that sphere. What it's doing, if you look at the bottom right of my screen, is it's running the script repeatedly, iteratively, all right? And so that's creating the second sweep hand, the minute hand, and the hour hand, because my computer thinks it's 11:56 in the morning in California, right? So if I stop running that script, Did I say no or yes? I forgot to say yes. You have to say yes to stop, not no, right? Obviously. There. This is the script. You see, so here is the XYZ points, which I could do exactly the same with a sine function. I could take my cantilever that I just constructed and take the top layer of atoms and apply a surface roughening to them, or I can do that computationally. I can then apply a force to those and have an iteration where I do a force, and instead of here just calling a displacement loop function, I could call a force field or quantum mechanical point calculation. So as I apply that force, I do it. Conversely, I could apply a velocity vector to those atoms and do the calculation there. So I could actually basically give them a rap like with a hammer and deflect the beam and see what happens with that. Multiple ways of doing it. Most important point that I want to leave this talk with is this is the Material Studio API definition. You can go into nearly any part of this and you just say, hey, I'm really interested in doing foresight APIs. What have I got? These are the sorts of tasks I can do with scripting, geometry optimization. I click on this. It shows me all the properties that I can access with a Material Studio script, and it shows me an example of the semantics that I can do to do that in Perl, right? And this is how you can do all sorts of extensions only within Material Studio to do the sort of interesting calculations that the question was about.
We have one more question. Is there a simple way to exchange data between Material Studio and MD codes such as LAMPS or NNIN?
Yeah, there are two different ways, right? The first way is basically you utilize these tools here, like the 3D atomistic tools within Material Script. Well, first of all, I can output PDBs and standard file coordinates, right? The second is that I can, run scripts that will output coordinates and output coordinate systems, right? So, for example, let's just look down here at this one and see if there's an example, right? So this allows me to output atoms, to output the position of those atoms, and I can output them in any format or layout I want beyond the base set that Material Studio supports, right? So again, Material Studio supports export in a range of different, that's a Perl file format, so it thinks it knows what it is. Sorry, give you a structure. Come on, show me a structure, be intelligent. So now it allows me to export these, right, in a range of different file formats, like shellx files, PDB files, right, etc. Other things that you can do are you can use Material Studio script, and there are multiple examples of this outputting to LAMP format and outputting to other formats on the Material Studio section of the Accelerist.org community website, and that you can use those scripts. The third way is that we also provide what are called Accelerist platform server tools underneath, which some companies and some organizations have access to from the Institute, and those allow you, we demonstrated, I think, earlier in the year, interfacing to things like LAMP and MD doing with that. So 3 different approaches. Write out standard file formats, customize the file formats using script, or extend using the Accelerist platform to do code wrapping.
We take one last question. How can I predict the crystal structure of a known compound using Material Studio before and after recrystallization? Can you use L-alanine as an example?
It would take a while to do that. The method you use is basically an extended iterative Monte Carlo approach. All right. Now, this is actually an area that there's been a lot of research on. There's been a lot of improvement in this. The methods, the broad approach, this sort of starts to touch on things like polymorph prediction. Things like L-alanine, we can also do with energy calculations. So it's actually one of the examples used in the NMR prediction calculations with Cascade NMR. this approach, right, and there are a variety of extensions and modifications to this, at its core requires the development of good intratomic, intra and intermolecular potentials, right, and charge distribution schemes. You then do a Monte Carlo packing type approach if you know nothing about the crystal structure, and that allows you to construct different configurations and to construct those different configurations subject to symmetry or not subject to symmetry in different symmetry space groups, to then do a Monte Carlo temperature ramp up. So basically you heat it up till it becomes a very low density system, and then you cool it down till it starts to crystallize, i.e. coalesce, i.e. the density starts to increase. You then accept a series of these and then apply full force field minimization to those. You then take those and save them, and then you can run them with material script through a range of different quantum mechanical prediction algorithms to put them on a common basis across multiple space groups and multiple areas. So that is one broad way, which is that I know nothing whatsoever about the crystal structure. I can start to make a stab at this. There's been a lot of scientific and academic groups working on this. People think, you may well know, this field, the blind test program at the CC Chemie Crystallographic Data Center. And there are a number of people who have done a lot about selecting novel algorithms. This is an algorithm that we put together a number of years ago. There's been some advancements in this, and now we're trying to think carefully about how we can extend this. And the algorithms involve the search step, so they involve the use of continuous and discrete searches and iterative multiple searches within those modes. If you know something about the structure, such as a powder spectrum, what you can do is to go to the modules. So I believe I have alanine in here. So if I go in and I just go back up to the structures, there you go. There's alanine, right? So I can take this structure and then I can start to also import data that's associated with that, right? Alanine spectrum. I don't know if it is. Okay. I have one of those. That's fine. So I don't have an experimental spectrum. But if I had an experimental spectrum, I'll just bring one in arbitrarily, right? What I can now do is to take this structure and go to my crystal structure reflex tool, where I can start to apply refinement approaches, which will allow me to look at things like my unit cell, my experimental data, my pattern, right? So I can start to do profile minimization. My lattice parameters, I can make these refinable variables, right? I can select my molecule here, right? Such as that one, and that fragment, and then I can go edit. I can define a motion group from that, right? So now I have what are called, as you see here, a series of ellipsoids, right? And now I can do let's just pick the pattern, do this. So that's called refinement. And then I can do an atom refinement on that. So that's the way of going through and doing a refinement where I have partial information. This might be a structure that I guess. This might be a modification to a known structure. So say I went in and I got rid of those motion groups, right? Just deleted those, and then I made a modification to that atom, right? So that is a way that I can do a refinement on the system. And there are a whole series of tutorials about doing that. That's one of the most important things about Material Studio, right? I can go in here and look at crystal refinement. So let's just find the one I want, reflex, right? So we'll do reflex here. We'll go into the reflex crystal tutorial. We'll do a reflex plus, right? And this allows us to look at these systems quite nicely. I can actually go down all the way to the bottom here, expand my tutorial list if I want to look at that, go to my reflex tutorials, right? I can understand refinement of a system, let's say, right? Or I could do a reflex plus, where I can actually add to the energy and the penalty, not just the difference between the calculated diffraction pattern for my structure and the measured. I can then add in a van der Waals function, right? So this tutorial, of which there are many, as you see in Material Studio, takes you through all of these systems, right? Calculating them, looking at things like the degree of crystallinity in a system, refining systems with energetic considerations. So here I'm going to build a molecule, right, with two flexible torsions, define those torsions, and then I'm going to do a reflex refinement on those. So you can do that. Material Studio drives that and supports that, and it's all done through this modules, reflex, right, reflex refinement interface, okay, when I set it up. So that's an answer. So again, two different answers to some of the questions that you've been asking. One about if you have no knowledge, one about if you have experimental information to use as a guide to the refinement.
I think we'll wind up with that. Thank you, Michael, for the presentation, and audience, thank you for logging in and listening to the webinar. Perhaps it was a tad long, but I'm sure it was very informative to all. Thank you, everyone, once again. Good evening and have a nice day.
Thank you very much, everybody. Have a great day.